This is a video walkthrough for the code for a one sample t-test. So to start, we will load our data. We are using the trees dataset, which comes as just part of R. So we'll load that up, and we're calling it an object called trees. So that's our data. Again, if we look over here in our environment, we see that under data, we have something called trees, and it has 31 observations of 3 variables. So to start off with, what we'll do is we'll get some summary statistics. So we'll use the summary function, which is a base R function again, and we're looking specifically at the height. So we're trying to see if the height is different than 72 feet, I believe. So we'll do a summary on the trees data frame, and we're saying, still like that, we're saying with this $sign right here that we just want the height column. Notice that I do have to capitalize this. Capitalization does matter in R. So we'll do this, and we'll see that the minimum is 63, the mean is 76, and the max is 87. Something else that we'll need is the standard deviation. So we'll go ahead and get that using the SD function, standard deviation. This is again in base R. And we see that the standard deviation is 6.37. We also want to see what our data distribution looks like. Is it normally distributed or not? So one way that we can do this is using a histogram. And so we'll be using ggplot. This is a package to do our graphing. It has a lot of flexibility, a lot of additional options. And so the first thing that we have to do is we have to call the package. If you have it installed, install it first if you don't. So we'll go ahead and call that. And then here is where we're making the plot. So in this first line here, we're calling the ggplot function. We are defining our data, so just the data set overall as a whole that we want ggplot to use. So we're saying data equals trees. So use this data in our environment right here. And then here, AES, that's aesthetics. And we have to define what our X value is. So we want to see how height is distributed. So we want height to be on the x-axis. And then we have a plus sign because we have another function that we're going to use, and we're going to say we would like you to please make a histogram. So we use geom histogram right here, and we don't have to put anything within those parentheses. The parentheses have to be there, but we don't have to put anything in there at this time. So once we have all this, we'll go ahead and run it, and over here in our plot window, there we go. All right, it just took a hot second. Over here in our plot window, we can see the distribution of height in the cherry trees. So we see a lot of them, only have one value, because on this y-axis again is count. So it says, how many are at this height, how many are at this height, how many are at this height. And so we can see it looks fairly normally distributed. It's not a large data set, so it's kind of challenging to tell exactly, but it looks to be relatively normally distributed. Something else we can do though to actually do a test of if it's normally distributed is the Shapiro-Wilk test. There is a function, the Shapiro.test function, which we can run, and we can run it again on that height column. So we'll use the Shapiro.test function, have the parentheses, and within that parentheses we'll put the trees, the $sign saying that we want just the height column. So if we run that, here is our output down here in our console. So it says, hey, you just ran the Shapiro-Wilk normality test on this data, it gives you the Shapiro-Wilk value right here, the W value. But what we're interested in is the p-value. So we see that p is greater than 0.05, which indicates that we do not reject the null, that the data are significantly different than a normal distribution. So we say, okay, that assumption checks out. Excellent. So then we can run the one sample t-test. So we will use the t.test function. Again, we're just looking at the height because we want to see if the mean height is significantly different than a specific value. And we define that specific value right here. So we say mu equals 72. Because our current research question is the mean height of the trees significantly different than 72? Is, let's see, 76 different? And so we'll run this. And here is our output. We ran a one sample t-test. Yep. And this is the data you ran it on. This is your t statistic right here, your degrees of freedom. And then here is the p-value. So p equals 0.001415. That is less than 0.05. And it tells us, here's our alternative hypothesis. And so since p is less than 0.05, we would reject the null that the true mean is, equal to 72. And it also gives us our 95% confidence interval. And it reminds us, this is what the mean is. Okay, so great, we have a significant test. We can also run a one sample t-test. So this one was just saying, is it different than 72? No other constraints on it. We might be specifically interested in, is it greater than 72 or is it less than 72? So we might have a directionality to our question. So again, we can run our t-test using the t.test function. We would define our data that we're doing it on. We would say, again, our mu, so the value we want to see if it's different than. But then what we can do is we can say alternative equals greater. And this is saying we want to know, is the mean of our cherry trees, the mean height of our cherry trees, greater than 72? And so if we run this, we see, again, we did a one sample t-test on the height, t statistic, degrees of freedom, and here is our p-value. So definitely less than 0.05. So we would say, that we reject the null and that the true mean is greater than 72. Okay, so it's significant, but how about an effect size? So we can calculate Cohen's d by hand, per se, or by putting in the actual values. And so what we're doing here is we're putting in the mean. So that's what 76 is. If we needed to be reminded of that, we could scroll up here and see, okay, here's our mean, so 76. We put in our mu, or what value we're comparing to. So that's 72 again, right here. And then we would need our standard deviation, which we calculated also already right here. And so we're saving this as just the object d. So we'll calculate that, and then we can print the value. So we see, okay, that's our effect size, Cohen's d, 0.62. It's a, decently large effect size. But there's also a package that can calculate this for us. The package is called effect size. And so we would first call that package, and it's loading and it says, okay, we loaded these things, thank you very much. And we can just calculate it using the package. So we would use the Cohen's _d function from the effect size package. We would provide it what exactly we wanted it to calculate Cohen's d for, and we also provide it with the mu. So we provide all these things, run it, and it says Cohen's d is 0.63. Here's your 95% confidence interval. So the Cohen's d calculated by the effect size package matches what we calculated up here, because it should. And we would say the effect size is 0.63, a moderate to large effect size.